going to talk about simple heating and cooling processes for atmospheric air. So a simple cooling or heating process is a process in which no condensation or evaporation occurs. Now, if you have evaporation, you'll be given that information. You'll be given that there's some means of introducing moisture into the air and that moisture evaporates. But for condensation, you need to be able to tell whether or not you have it. And I say here that it's just in a cooling process. You'll see why I don't also say heating process as well in just a second. So in this class, we'll consider the very common scenario that you have relatively constant pressure heating and cooling in ductwork. So with that being said, one thing to keep in mind, if you don't have any condensation, because your mole fraction doesn't change, if your pressure does not change as well, so your mole fraction and your pressure are constant, then your partial pressure is constant as well. So what we're going to do is we're going to follow along on a TV diagram the behavior of the water that's still in that atmospheric air, that's still in a gas phase. So I'm going to draw a line of constant vapor pressure, and I'm going to start out there in the superheated region. So my water vapor exists as a gas. It's going to be superheated, and if I heat things up at constant pressure, well, there's no condensation because I'm still in that gas region, the superheated region, nowhere near that saturated vapor line. So still along the line of constant vapor pressure if I'm heating at constant pressure. And so you can see for any heating process, as long as there's not any means of introducing moisture into the air, this is a simple heating process. Now, cooling is a little bit different. You need to be cognizant of what the dew point temperature is. As long as you cool at or above the dew point temperature, you don't have any condensation. But if you do cool below it, then that's a different story. So let's take the scenario where we don't cool below the dew point temperature. We're at or above it. For a simple heating or cooling process, the specific humidity is going to be constant because the ratio of the two components in that atmospheric air, your water vapor, your dry air, are going to be constant because you don't have any condensation or evaporation of water vapor. And now the relative humidity is a little bit different. As for a simple heating process, as your temperature increases, the saturation pressure is going to increase. And so since the denominator is increasing, the overall value of your relative humidity is going to decrease. And of course, for a simple cooling process, it'd be the opposite. Now let's look at how we model it. So what we're going to do, we're going to apply the conservation of mass, and we're going to apply it to each component within our mixture. So for the dry air, I have dry air coming in, and I've got dry air coming out. So dm dt equals the sum of the m dots coming in minus the sum of the m dots going out. Sorry, that should be m dot. The last term should have a little e under there for exit. But if it's occurring at steady state, what that tells me is that the mass flow rates at the inlet and the outlet are going to be the same. So m dot a at the inlet is equal to m dot a at the outlet, and I'm just going to call that m dot a. Now for my water vapor, it's the same story. So dm dt goes away, and I've only got one outlet for the water vapor as it goes in and out. So m dot v1, m dot v2, those are equal to one another. It's just equal to m dot v. And now I'm going to apply my energy balance. So here's my energy balance. It's an open system. A lot of things are going to go away. So steady state, no work, no changes in kinetic and potential energy changes. However, I am capturing the fact that, well, in this picture right here that I've got a cooling process because I'm removing heat from the air by means of a cooling coil. Of course, my Q could be going the other way. It could be going into the moist air, and that would be for a heating process. But the point is, the way that I've drawn my boundary, I've captured the fact that I do have heat transfer. So the heat transfer term does not go away, but it's equal to the sum of the m dot h's going out minus that going in. So I've got dry air coming out, dry air coming in. And I've got water vapor coming out, water vapor coming in. And now what I'm going to do is I'm going to realize that the mass flow rate of the air at the inlet and the outlet are the same. So I'm going to just kind of bring that outside of the parentheses there. Same thing with that water vapor. And now I'm going to divide through both sides of that equation by m dot of the dry air. And that would give me units of kilojoules per kilogram of dry air. And you'll see why that's useful in just a second. So you could see that that m dot a in front of the first parentheses, that of course got divided out. And then m dot v over m dot a, well, I'll recognize that as just the definition for the specific humidity, and the specific humidity at 1 and 2 are exactly the same. So let's see, there we go. I've rearranged things, and I brought in a new term, the specific humidity, which is something I might know. And then I'm going to rearrange it just one step further. and put it in terms of the specific enthalpy of the moist air. And that's something that I can actually look up in my psychrometric charts. So that would be very useful for me. So options for solving. Well, if you are at 1 atm, you can absolutely use those psychrometric charts. But if your pressure is not at 1 atm, you have to use the thermodynamic tables for water and air to look up those H values. And you have to calculate what your specific humidity is based on the equations on your equation sheet. It doesn't mean that if you're at 1 atm, you can't still do that. It's just a little bit more work. So if you have to use your thermodynamic tables, you can look up your H for the dry air in your ideal air tables. You can look up your H, your enthalpy value for the water vapor in the in your steam tables, and you need 2 independent intensive properties to fix your state. So you've got temperature and pressure of the water vapor, but for atmospheric air, we simplify things and we just say, just approximate it as H sub G at T, and that way you're not interpolating in those superheated tables or anything. And that's valid for the low partial pressures that you're gonna find in most air conditioning applications. One word of warning: don't mix and match these options. If you start out solving the problem with the charts, finish it solving with the charts. If you use the thermodynamic tables, if you start out doing that, continue solving with the thermodynamic tables, if you're at 1 atm. And the reason is because that specific enthalpy of the moist air that's tabulated on, or that's on the psychrometric charts, the values there those are not the same values that you would get if you looked up the H value and the HV value and that specific humidity. You calculated the specific humidity at that whatever state that you're at, because in the thermodynamic tables for dry air and water, they use 0 Kelvin as a reference point, meaning that the H value is 0 at 0 Kelvin. However, for the psychrometric chart, they use 0 degrees Celsius for a reference point. And so since those reference points do not match, you can't merge those two together. However, the difference between H1 and H2, or the specific enthalpy of the moist air at 2 minus 1, will be the same using either method. So if you solved a problem where the pressure is 1 atm using both methods, use the psychrometric charts, finish the problem, then redo the problem with the thermodynamic tables, and you compare the answers, you should get a pretty close answer. Of course, when you read those charts, and I'm blocking that. Let's see. There you go. You read that, right? But if you do, there's going to be a little bit of error when you read those tables. So they won't be exactly the same, but they should be pretty close. All right. Thank you for watching. Let me know if you have any questions.